Hey everyone, and welcome back. In this video, I'm going to be covering 3 of the web challenges from UIUCTF, specifically peanut-xss, adminplz, and futuredisk. I did not solve any of these challenges. Instead, after the CTF ended, I found some notes on Discord, specifically these notes from Mini3Oat, Molin, and Molin discussing these 3 challenges, and I went back and solved them and had fun, and so I'm making a video, and hopefully it's useful to other people too. And with that, let's get started. This is peanut-xss. It says Nutshell is pretty cool, want to test it out. So Nutshell is a library for embedding expandable content. And what that means is it creates these little links. And in here, when you click on them, it kind of creates this content below it, these little content bubbles. The bubbles can be recursive, and so you can keep clicking down and down and down. You can embed content from YouTube, Wikipedia, other websites, barring some same origin policy issues. And the idea is you just include this JavaScript snippet, and as long as a link has these the double dots, it will be expandable. The goal for this challenge is we need to basically XSS it. It tells us that the flag is in a adminbots document.cookie. To interact with the admin bot, you just netcat to the port that was given here. So we need to create a URL such that the admin bot will go to it and it'll leak out their cookies. And we have a little play area here. It says to write a section, use headings and paragraphs, and then make a link. This is linking to this section. So to write a section, just does kind of like a slugify. And then since it begins with this, it'll be converted by Nutshell into a special section. And so if we create it, this is that same content, and we can see this is the embedded content. And it says just use headings and paragraphs like this, and just use headings and paragraphs like this. So it was able to embed this content. We can notice we're still on the challenge site. It just embedded all the content here. For this, there's 2 things. It says it uses DOM Purify. DOM Purify is being used twice. Once on the actual challenge server, and it's also being used within Nutshell itself. So we have right off the bat, it's going to read whatever this Nutshell parameter says, and then pass everything into DOM Purify, which definitely makes things a little bit more difficult. Cool. For actual exploitation, there were 2 bugs. So this is Nutshell.js. I just dragged it out so we had syntax highlighting. There were 2 different ones. There was one on the YouTube. So if we go to YouTube, I think actually no cookie. Yeah, the video ID parameter was injectable. The problem with this is you needed to have user interaction. So I spent quite a bit of time trying to get user interaction, and based off of Discord, it seems like a lot of people did. So this was not the correct path. The correct path was there was an inner text that maybe it was up one. Nope. It might be this one. Convert links to expandables. I think it's this one. Basically, it copies out as it's creating those links that we can click on to expand text. It's going to pass a inner text element as a inner HTML. I passed over this at first because I thought inner text, the key to this was realizing that if you were to pass in and LT, obviously this is a less than bracket, but it's not actually going to be rendered. I mean, it's going to be viewed in the browser, but it's not going to be treated like a less than bracket, so you can't put real HTML content in there. But inner text, when it sees one of these, it'll actually return this instead. Like it's returning the text that you would see. And this is where the bug exists, and why I unfortunately initially passed over it, is that, yeah, it doesn't return, when you pass and less than, it doesn't return this, it returns this. So we have just a very basic XSS right here. The link text.innerHTML will be equal to this, but rendered for us, which is amazing. To see what that looks like, we can go back to the example, and maybe like right here, we'll do and less than, we'll do an image, source is equal to x, on air is equal to alert1, and greater than. Oh, we're missing this. Image, source equals x, on air, alert1, greater than. So we'll see if this works. Preview, and there we go. We have an XSS. So once you realize that, the rest of the challenge is very simple. We just need to leak the admin cookies. To do that, I think I have a little exploit somewhere. Yeah, this is what I ended up using. So image on air, source is equal to x, on air window location is equal to this webhook site. Then I encode the cookies. So really nothing too special. You just take this, you can plop it into the web page. So we can just plop it right here. Oops. Once, let's see. Hopefully I caught it in time. So I copied the URL out and it worked. Cool. So then we just give this to the admin bot. I already have the URL right here because we need to copy this out too. So we copy the admin bot. Let's open up a netcat. Let's specify a URL. Give it to the admin bot, and let's go look at our webhook site. Do we have it open? Nope. Webhook.site. Let's see if we have any recent cookies. And we have a recent cookie. It says UIUCTF, cracking open some nutshells. So already sent to us, so fun challenge. This is web adminplz. It says your daily dose of copy, which is Java. We're given an instancer link and a download file. This is what the web app looked like. It says only admins can access the flag. We're given a login form and a report form. So the idea behind this challenge is there's a log file, and we're able to leak sessions, specifically cookies, into this log file. And the attack we're going to do is we're going to do some dangling markup injection attacks in this log file, and we're going to treat the log file as HTML, such that we're able to exfiltrate data from this log file. The reason we have to do this is CSP is enabled on this web page, and it's CSP default source none, which means basically we're not going to get any XSSs or anything. All the fun happens in this log file. Cool. Some other stuff, like I said, this is a Java app. Thankfully, the app is really small. We're allowed to log in as any user. It's going to do some is-admin checks. There's that report URI, or sorry, that report URL. Nothing too exciting. It's just going to spawn a bot.js. The bot.js, all it does is it logs in as the admin user, and then goes to the page that we send it. On the web server, there's a flag.html, and this is our target, which contains the flag. And the exciting route is this /admin route. And so this is pretty much where all the fun stuff happens. You're allowed to specify a view parameter. And if the view parameter contains the flag, it's going to put this into the log. And it's specifically going to put the username into the log and the session.getID, which turns out to be the cookie value. So we're going to have usernames and cookie values put into the logs. After that, if you're an admin, you get to view whatever file was requested. Otherwise, error.html will be sent. So like I said, we're going to do some trickery, and we're going to inject a bunch of stuff into this log file, and then later we're going to render this log file as HTML, and we are going to be able to use a dangling markup injection attack to leak stuff from the log file. So first, like I said, we're able to inject interesting stuff into this log, and specifically, since we can use the bot.js and view anything, we're going to have bot.js log in as admin, then we're going to trip this logging warning so that admin's cookies will be injected into the log file. So somewhere in there, it's going to say user, admin, and the admin cookie attempted to access a restricted view. So we have admin cookies there. If we can somehow exfiltrate that, we can log in as the admin on the web portal, and then we can view any file, including the flag file. To exfiltrate it, we're going to do a dangling markup injection attack, which is pretty fun. There's a couple of different ways to do this. I think the common one is using meta refreshes. So I forget the exact syntax, but it's a meta, let me look at it real quick. HTTP equiv refresh, is it content? Yep, content 0 URL is equal to HTTPS webhook.site. Okay, cool. What we're going to do, so this is a dangling markup injection attack, and so basically we're not closing out, we're not including these 3 characters initially, and the meta tag, this is an HTML tag, it's going to be looking for the final 3 characters. And what we're going to do is we're going to supply those later. So first we're going to insert something into the log that looks like this, and we're able to insert this string into the logs because we can specify any username we want. And so we're going to say user with this username, this very janky username, and it'll have, the session cookie and stuff we don't care about. But when the browser reads this, or bot.js reads this, it's just going to keep reading and append everything in here to this URL. I guess we should do it like this, data is equal. It'll append everything until it sees closing brackets. And so we're able to, if we can inject juicy stuff in here and then the closing bracket, we should be able to exfiltrate everything in between. So we're going to put this as the username. Cool. Then we're going to do that other thing where we're going to log in as the admin, and we're going to have the admin view some flag file or some file that contains the word flag in it, or the file name contains flag, so that it'll leak the admin cookie. Admin cookie will be here. And then we're going to register another user with the username of this. And then we're going to have the admin bot go back and view this log file as HTML, again, using this resource. It's a very multi-purpose resource. And so that when they see this, they're going to say, okay, refresh, go to this URL. It's going to include all of this stuff. And in here will be the admin cookie, and it'll get sent to our webhook site. And that's the exploit. So putting it all together, this is what it looks like. Let me actually start it in the background because we have to wait like 5 minutes. Python 3 solve.py. Error, no found path. Oops. Okay, it's starting. So we have the base URL, we have our webhook URL. This is our initial username, meta http equiv, refresh, content, URL, webhook, and then here's our leak. So we're going to log in as that user. I just print out the session cookies. Then we're going to make sure that this username is logged by doing the /admin view flag route, and so it'll be in the log file. Then we're going to embed the admin cookie. We do that by going to report, which will spawn up that node bot.js as the admin user, and we'll have the admin view a file with the name flag in it. And so now the admin's cookies will be in the log file. Then we're going to sleep a couple of seconds, and then we're going to register a new user with the username of quote, quote, bracket. And that way it'll close out the meta refresh. In the code, we have to wait 5 minutes for in between requests to the admin bot, so we wait 5 minutes. And then at the very end, we request the bot to go back and view the log file. This is the log file, and that way it'll get rendered as HTML, and it will see that meta refresh, and the session cookie will be leaked into our webhook, our webhooks.site. So I let it run. Like I said, it takes 5 minutes, so we just have to wait. Sweet, and it's done. So we can check out our webhook. We have something here. It says blah, 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 attempted to access, and here we go, user admin. This is the ID, attempted to access restricted thing. So we have a admin cookie. So let's log in as a submit. That way we have a cookie. We'll go to edit this cookie, jsession. We'll change out this cookie. Then we're going to go to admin view is equal to file flag.html. And there we go. Let's close all this crap. It says, admin, please, can I have some more cookies? So pretty fun. This is web futuredisk. So we spent a bit of time on this challenge, and obviously we did not solve it. But it was a pretty fun challenge. I feel like it's more of like a reversing challenge than a web challenge, but it is what it is. So it says we mounted a 10 exabyte flash drive. So exabytes, so there's kilobytes, megabytes, gigabytes, terabytes, petabytes, and then exabytes. Hard drives are like terabytes, so this is not realistic, absolutely huge. They create an 8 exabyte file called haystack.bin. Somewhere in there they put the flag, and then they gzip it, and they put it on an Nginx server. So cool, and so somehow we have to download this file or something and get the flag out. To solve this, a bunch of different tricks had to be employed. First, in HTTP, there is a range header, which allows us to download arbitrary chunks of a file. And thankfully, this is hosted on Nginx, which supports the range header. So we can download little chunks from this file wherever we want. We just need to know where we want to download. The next thing is we kind of need to understand the gzip format. So there's these diagrams created by, I'm not sure if it's Angie or Ange, but they make a bunch of these diagrams and they're all amazing. And so this is the gzip format. We can see that it starts out with about 10 bytes of headers for the gzip stuff, but the actual compression in a gzip format is done by deflate. And I think the trick to realizing this this challenge was realizing that deflate, it compresses into these blocks, and since most of this file is all zeros, all the blocks will be exactly the same size. And because of that, we have this repeatable pattern, and we can do a binary search on it. And so the idea is each one of these deflate blocks is about 8 kilobytes. And so if you were going to ask for, give me the 10th block, you should see a deflate header, and then you'll see the data. And all the data should be the same because it's all null bytes. But if you search, you go 10 bytes blocks out, you should see a header. If you go 100 blocks out, you should see another header because all the blocks are the same size. And so you should always be seeing headers until we encounter the block that has the flag. The flag block will be a slightly longer length because it's going to do the Huffman encoding and put the Huffman encoding tree in that block. And so because of that, that block will be a little bit longer. So if you were to ask for, like the 101th block, for example, and that's after the flag, if you're saying the block size is 8 kilobytes and you look for the header there, there's not going to be one because that flag block right before it was a little bit longer. And so it's going to be at a different offset now, and there won't be a header where you expect there to be a header. And so using that knowledge, we're able to do a binary search and figure out specifically where the block is with the flag. To to see what that kind of looks like, let me go to this. Let me clear all this out. Actually, let's take a look at this first. So let's take a look at what the contents actually look like. So we're going to do a curl, a range. We're going to ask for the 0th byte to the 10,000th byte of the gzip, and we're going to pipe that out to hex dump. So we'll write it here, do a curl. And so this is what it looks like. These are the first couple of bytes. So this is all like the metadata, just setting up the file. And this is what a block actually looks like. Most of a block is all just 5s. So this is a uppercase U, separated by a little bit of metadata that is not all 5s. I guess it actually probably starts here. And so this is what a header looks like. And then the rest of it's just U's. And then for 8 kilobytes later, there's going to be another one of these headers, and then a whole bunch of U's. And it's going to continue that billions and billions and billions of times. So like I said, we can do a binary search on that because as long as it's all zeros and we haven't encountered a flag yet, all the blocks are exactly the same size. And that block size is actually this, 8,204 bytes. And because it's bit aligned, unfortunately, it means it's actually 0.25 bytes, which leads to a fun complication. So doing that binary search, let's say the file was a little bit smaller. We would start with index of 0 and end of like 200, let's say. First thing you do is you calculate the midpoint. We know somewhere in here, let's say there's only, we're assuming there's only 200 blocks. Really, there's a lot more. But we know that the flag is somewhere in this file. And at the end, obviously, things are going to be kind of wonky. They're not going to be aligned because the flag has occurred in there and it's at a weird size block. And obviously at the start, the flag hasn't occurred. So every block is going to occur every 8 kilobytes or so. So what we do is we calculate the midpoint. In this case, it'll be 100 right in the middle. And we check the header here. If there's a header at this location, we know the flag has not occurred yet. And so when we send it over to do the range request, we're going to do 100 times 8204, 8204.25. We're going to ask what bytes are here. If there's a header, we know the flag has not yet occurred. And if there isn't a header, if there's just random zeros or U's for it means data, we know that the flag has already occurred. So let's say the flag hasn't occurred, so that means midpoint is equal to 100. We can continue this algorithm and we'll say the start is equal to 100 and end is equal to 200 because we know the flag must exist somewhere in here. And so now the midpoint will be 150, and we'll check the 150 midpoint. If there's a header there, we know the flag must be on the far side. If it's messed up, we know that the flag must be on the previous side. And yeah, we just keep digging down. So the time complexity is going to be some log base 2. And eventually we should find the block that has the flag in it. This is what the solve script looks like. It's really messy. I'm not going to cover most of it. I'm just going to cover, that's the main idea. The rest of it is just, an exercise in programming. There's a couple fun things. First, like I said, deflate works on the bit level, not the byte level. And because of that, you're going to have this weird, 0.25, which just makes things a little bit more difficult. You need to be careful about rounding and stuff like that. Also, because we're dealing with numbers that are so large, eventually the floating point precision wasn't good enough to handle this 0.25. So I needed to convert things to decimal.decimal. That was an annoying bug to debug. There's also the trickiness of knowing if you're actually at a block header, because there's a couple of different block headers because things are bit aligned. One way to do that is to just record what a bunch of these block headers look like. There should only be 4 of them. So just kind of ask for that data and add it to a known signatures set. And so that way you kind of know this is a signature or this is not a signature. Otherwise, after that, you just do the binary search. And eventually you should just find the block that contains it. So I do that binary search. I just check if the midpoint has a valid header or not. If it does, I update the start and end. I work off of indexes instead of raw bytes just to keep things a little bit cleaner. You just need to be careful if you're dealing with an index or if you're dealing with an actual byte address. Once I'm done with the binary search, I just print out from -3 to 3 of those indexes, and eventually we should see a block that looks very different than the rest. So if we run it real quick, Python 3 solve.py. This is what some of the indexes, some of the block headers look like. They kind of look like this, and then they end in all U's. I do -1, so all of them start with a U just to kind of know I'm aligned correctly. But we can see this one starts with an A, EF, 15, D8, and then we reset again. So A, EF, 15, D8. Like I said, that's just because things are bit aligned. And now we're starting the binary search. So I'm starting at 2. This is the end index, and so I'm calculating the first midpoint. This is the data that was here. Then yeah, I pretty much just go through and update, and eventually it should converge on some point. And slowly it converges more and more and more. and then it finished. So it says that it thinks that it is right here. So this block index has a very weird header. So I subtract a couple and I just print them out to make sure everything looks good. So we're still getting U's, which is good. So at this block index, we get a U, that looks good. We get another U, that looks good. We get another U, that looks good. At this one, things look strange. This is a very large block header. So most likely this is the Huffman encoded flag. Huffman encoding, I guess I didn't really talk about it, but it's just a way to compress data. It uses like this neat little tree thing and does some like optimal encoding sort of stuff. But anyways, this block index looks very interesting. So next we want to download this block index. So I have a separate script for that. I think I call it dumper. Yep. So I'm going to curl. So this is that index. I convert the index into the byte address. So this is the byte address. I request 10 kilobytes at this address, and I send that to dump.gz. And I'm just doing it in curl. So we can run that real quick. Python 3, dumper. I just save it. Next, I guess I probably should have talked about this earlier. How did I know that it was 8 kilobyte block size? I found a tool online, this one, written by Paul Sladen, really good. This decodes gunzip files and it prints useful stuff out for you. And so it works on Python 2.7, but if you do decoder, maybe it was bin.gz. Yeah, this is it. I just enabled all the print statements and I can kind of go through the format and it'll tell me like just a lot of interesting stuff about the file. So we can see there was a new block starting at this byte 8213. And if we keep going, eventually we'll see a new byte started at 16417. And so this is roughly where I knew the block size was, just super useful for debugging. And so that's how the block size is calculated. Now that we have the specific deflate block that has the flag, we still need to decode it somehow. I just modified this decoder script so that instead of working on a gzip, it just works on deflate boxes, since I knew it kind of worked for this. So I think I did decoder deflate, yeah. To do this, basically, I just commented out a whole bunch of stuff that was doing parsing of the gzip stuff. So this is all the gzip parsing. We don't need it anymore. Really, we just want to decode the deflate boxes. You also have to do you comment some other stuff out over here because it does some like magic byte searching. Obviously, this is not a gzip. This is just like a raw deflate. There's one other thing you have to do. Normally, this line isn't here. It's reading from a bit stream. Again, deflate works on the bit level, and so you just had to guess. You had to read a couple of bits off the start. Eventually, I found out it was 5 bits in is where this particular deflate block started. Not too exciting, but something to keep in mind. So decoded deflate, we run it. It's a 2.7 script. It's an old script, and we also need to pass it dump.gz, and it should start reading. And it crashed because we don't have full bytes. But here we go. It printed out the flag. UIUCTF binary search means searching a binary stream right. So pretty crazy challenge. There's even a harder challenge, futuredisk 2. I looked at it. The block sizes are not consistent, which just seems terribly difficult. So props to the 8 people that solved it. Very impressive. But I didn't want to subject myself to that type of pain, so I don't think I will be doing it. But yeah, amazing challenges. Thank you, and I'll see you at the next CTF. Cheers.